Welcome to another Advent of Code walkthrough video. Today we'll be looking at 2022 day 22. Okay, so the monkeys take us on a trail through the jungle, and we're even going in about the right direction according to the GPS. As we walk, they explain that a grove is protected by a force field, and to get through the force field, we need to enter a password, which involves tracing a path through a strangely shaped board. At least that's what we think we have to do because the elephants aren't fluent in monkey. So they give us the notes that they took when they last saw the password entered, which is our puzzle input. So we get some sort of a grid and a string of moves. The first half is a map of the board, which is a bunch of open tiles which you can move on, which are dots, and solid walls, which are pound signs that you cannot move through. And the second half is a description of the path, which follows alternating numbers and letters. The number indicates how many tiles to move in the direction we're currently facing, or until we stop at a wall. And a letter indicates if we turn 90 degrees clockwise or counterclockwise, and turning doesn't change where we are. So 10R5 would mean move forward 10 tiles or until we hit a wall, then we turn right, and then we go forward 5 tiles. We start in the leftmost open tile of the top row of tiles, so in this case that would be right here. And we start facing right. If we would go off the board, we wrap around to the opposite side of the board. So for example, in this test case here, if we go right at A, we would end up where B is, and if we go down at C, we end up where D is. It's also possible for the next tile to be a wall, in which case it counts as the wall being in front of us, so we stop before the wrap. If we draw which direction we were last facing, each time we get a path that looks somewhat like this, so you can trace the path just to see how it looks. And to finish providing the password, you need to find your final row, column, and direction. The row and column are both 1 indexed, and the facing direction is 0 for right, 1 for down, 2 for left, and 3 for up. And the final password is 1000 times the row plus 4 times the column plus the direction. Given this, what is the final password? Okay. So the first part is to get the grid itself. So we'll do for line in open 0. We'll chop off the new line at the end. If the line is a blank, then we will mark done equal to true, which tells us that the grid is done. So now when we read in a line, if we're done already, then that line is the sequence of moves. Otherwise, we'll append it to the grid. And so this is what we would get for the grid. So that's our grid, and our sequence of moves is that part. Okay, so we need to start at the leftmost open space in the top row. So our row starts at equal to 0, and we start the column at 0 and then do while grid RC is not equal to an open space, we increment C by 1. So by doing that, we will find the first open space in the top row like so. Now we basically just proceed with our movement steps. So we'll use regex to get the movements out. re.findAll will find all matches. In this case, what we're looking for is a sequence of numbers followed by either R or L, which is optional because the last move will not have a letter after it. And so for x, y in re.findAll sequence, we can print out x and y to see that this is our output. So y is undefined at the very end, or rather the empty string, which is perfectly fine. And so we want x to be an integer. So now we just do for blank in range x. What we'll do is we'll move r and c forward. So dr is equal to 0 and dc is equal to 1 initially, which means that we are not moving our row, and we are moving our column up by 1, which would be to the right. So here we can do this. While true, r plus equals dr and c plus equals dc, or rather r equals we also need to wrap around. So modulo the length of the grid, and C equals C plus DC mod the width of the grid. Oh, and just one other thing. The input doesn't seem to have padding, so this can and will cause issues. So let's just pad our grid. So how do we want to do this? Width is the maximum of all of the lengths of the rows, and then we can just do grid equals line dot, what was it again? Line plus space times width minus length of line for line in grid. Okay, so what this does is this gets the largest length in the grid, which would be the width, and this takes each line and pads it with spaces equal to the how many spaces we're missing, basically. So this will make sure that our grid is adequately padded so that we won't get issues. We kind of need our board to be a rectangle here. Okay. And so now we just say if grid RC is not equal to space, then we break. So what this is doing is we start by moving in the appropriate direction once. If we hit a space, that means that we're currently off the grid, so we keep going until we wrap back around. And so until we hit a space, we just keep repeating this and stepping forward until we eventually will wrap around. Now if grid, let me change this up a bit. NR equals R and NC equals C, that will be next row and next column. Okay, so if the grid at NR and C is equal to a pound sign, then that means we've hit a wall. So we will break and not apply the move. Otherwise, if we don't hit a wall, then we can do R equals NR, C equals NC. Basically, we will commit the move. So we first step forward until we're back on the board, and NR and C is where we will end up. If it's a wall, then we break out immediately, and if it's not a wall, then we commit to the move. And now we do the turn. So if y is equal to r, then dr dc is equal to dc negative dr. And if y is equal to left, then dr dc is equal to negative dc dr. This can be a bit tricky to reason with, but you can work it out in your head. It's always going to be you swap the column and row and then invert exactly one of them. Which one depends on your definitions. So in this case, positive dr means moving down. So if we turn right, then our positive dr will become a negative dc, and so we know that this is negated. And similarly, if we turn left, then down becomes right. So the dc would become the positive of dr. And so the other one would have to be inverted. And now we print out RC and our direction just to make sure everything is correct. So we end up in we end up in row 5, which is correct because we're using 0 indexing, and column 7, which is also correct. And the final facing direction is right, which maps to 0. And our row index of 0 and column change of 1 maps to right, so that looks correct. Okay. And now we just need to map this to the actual output format. So we'll do k is equal to, so if dr is equal to 0, then if we're going to the right, k is equal to 0, and if we're going left, then k is equal to 2. Otherwise, if we're going down, k is equal to 1, and if we're going up, k is equal to 3. And so now we just need to print 1000 times the row, which will adjust for 1 indexing, plus 4 times the column, plus k. And that gives us our final test output of 6032 and the puzzle answer of 47462. Now when looking at this, I was like, why are these gaps in these specific places? This looks a lot like 6 square setup in the net of a cube. And unfortunately, that is exactly what it is. For part 2, you have to fold up the map and like a cube, and all of your edges have to warp around. So this is very confusing to visualize, which is why I have the whiteboard out today. I will ignore the test data entirely and focus only on this. And correct me if I'm wrong, but I think everyone has the same shape of input today, which means that my solution will work for everyone. Okay. So let's draw out our board. So we have the shape of our input, which we'll use by inspect by looking at the right side here, is so that's what our output looks like basically. So now, the trickiest part about this problem is visualizing exactly how these edges line up. To do that, I think the easiest way is to mark every corner and line up the ones that are the same. So obviously these three corners are already the same. Each corner will have three faces touching it. So keep that in mind because that's really helpful. So let's start with just some random corner here, and let's label it 1. So this corner is 1. Where is it connected to? Well, it's actually a bit hard to tell right here, so let's move on to a different one. This one, let's call it 2. So we can clearly see that these two edges will line up when we fold up the cube, and so that tells us that this corner is also 2. And since this gives us 3 faces, then corner 2 is complete. And so when we line up these, then this edge here will line up here. And so since this is corner 2, this would be corner 1. And so now we also have 3 faces lined up for corner 1, so that's done. Now let's move on to, say, this corner, just because it's easy. This one lines up with this. And notice here that we only have 2 now, so there's another instance of corner 3 that we're missing right now. Let's move on to that later. This is 4, so these two line up like so. And then when we line up these edges, this face will like get rotated in here, and then this face will get rotated up here, and so these two will fold together, and so this edge and this edge line up. So this here is corner 3. And so that gives us our instances of corner 3, and the last one is just here, corner 5. Each cube has 8 corners, the remaining 3 corners are here, and these are pretty easy to tell because they're already lined up for us. Okay, so now we just need to match up the numbers. So, for example, this edge here, 1, 2, lines up with the other edge, 1, 2. And you'll notice here that it's flipped, so when we warp, we'll jump to the opposite side. So if we start up here, we go down here, and if we start down here, we go up here. So we just need to be careful with our rotations like so. Okay, so how exactly will we do this? Well, now instead of running our while loop to jump back around, we'll just do nr equals r plus dr and nc equals c plus dc. And now we basically just need to code in all of the cases for our jump. So unfortunately, this is a rather tedious process. There's almost certainly a better way to do this, but it would honestly have taken me much longer to actually think of a smart way. So I basically just hard-coded all 14 possibilities. It actually isn't too bad. It would have gotten me top 10 if I didn't have one small bug that I didn't catch until like an hour later. So here we go. So we'll do each edge in pairs just to make things a bit easier for us. Let's start with this edge here, the edge 1, 5. So this edge lines up with this edge. So the condition for if we've gone off the top edge is if the row is less than 0 and the column is between 50 and 100. And we're currently moving up. Then in this case, we end up moving right, so we set dr equal to, we set drdc, or sorry, not drdc. Actually, yeah, let's just proceed with this for now. drdc equal to 0, 1, indicating that we're now moving to the right. And we also need to change where our row and column are. So in this case, since our edges aren't facing the same direction, we will need to flip our coordinates. So NR is the hard one, but NC is easy because our column ends up just being 0 when we arrive here. The row, however, is a bit more difficult, but one convenient thing is we can imagine drawing a diagonal along the board here, which we'll actually leave in because it's convenient. And if we just do NR NC equals NC NR, we will flip ourselves directly over this. So if we say NR equals NC, then we end up here, and the edges are lined up properly like so. So we just need to shift it down by 100. So it'll just be NC plus 100. Okay, that's 1 of 14 done. Let's move on to the opposite side. So the condition for this one is if the column is currently less than 0 and the row is between 150 and 200, and we're currently moving to the left, then our new direction will become down, and NR and NC, we can just invert this operation basically. So NC is going to end up being NR minus 100, because if we flip this over, we go here, so we just need to shift to the left by 100, and NR ends up being 0. Okay, so that's one pair out of 7 done. Let's move on to this one, the 5-3 edge. So for this one, we actually don't end up like flipping the direction, so it's not like this. They actually just line up parallel like this. So this one's actually one of the easier ones. The condition for the top edge is if NR is less than 0 and NC is between 100 and 150, and we're going up. In that case, we actually still are going up, so we don't need to change our direction, and NR and C, the row is just set to 199, the bottommost edge, and NC is just NC minus 100, because we just need to shift to the left by 100. And equivalently, if NR is greater than or equal to 200, so that's if we hit the bottom edge here, and NC is between 0 and 50, and we're currently moving down, then we map to the top edge here, so we stay moving down, and NR and C is equal to 0, NC plus 100, because the row when we arrive here is 0, and our column is just shifted to the right by 100. Moving on to the 3-4 edge, this one is a bit trickier because we have it upside down, because these two line up like so, and so you have to remember to invert them like that, which actually isn't very hard. It's just 149 minus NR, because 149 is right here, so if we have 0, then 149 minus 0 gets us here, and as we move down and increase the negative, we also decrease here. So the condition for that is if NR is between, if NC is greater than 1 or equal to 150, so if we've hit the right edge, and NR is between 0 and 50, and we are currently moving to the right, then we will end up moving left, and we will need to change our row to 149 minus our row, and our column ends up at 99. And then let's do it from this side as well. If NC is equal to 100, let me draw some markers just to make things easier actually. Okay, so if NC is equal to 100 and NR is between 100 and 150, and we're currently moving to the right, then again we'll end up moving to the left, and now NR and C, The 149 minus nr operation is symmetric, so we do that again. And NC now ends up at 150, so 149, because we're one less than that. Moving on to the 4 edge, this one here. For this edge here, to check if we're going down, the condition is if nr is equal to 50 and nc is between 100 and 150, and we're currently moving down. Then we'll end up moving left, and this one is a bit tricky to calculate. The column number will always end up as 99. And the row number, again, we can imagine us flipping it. So if we took this and just flipped it directly, we'd then need to shift the row up by 50. So it'll be NC minus 50. The condition for this way is if NC is equal to 100, and NR is between 50 and 100. And we are currently moving to the right. Then we will end up moving upwards. And we just need to invert our operations. So the row will end up at 49 this time, and the column will just be nr plus 50. You can also imagine that by using the flip method. If we flip this, we get this, so we need to shift it to the right by 50. Alternatively, you just observe that nr equals nc minus 50 means that nc equals nr plus 50. They're the opposite. Moving on to this edge here, the condition for the downwards method is if the row is 150 and the column is between 50 and 100. And we are currently moving down. In that case, we end up moving left. And our row, if we flip this, we go here, so we need to add 100. So our row is our column plus 100, and our column always ends up at 49. In the inverse direction, the condition is if the column is equal to 50, and the row is between 150 and 200, and we are currently moving right, then we end up moving up, and we invert the operation. So nr is now always equal to 149 here, and if nr equals nc plus 100, then nc equals nr minus 100, which we can also observe by flipping this over to here, and then we need to shift to the left by 100. This won't take too much longer, I promise. We just have 2 more pairs left to go. For this pair, the condition for moving up like this is if nc is equal to 99, sorry, nr is equal to 99, and nc is between 0 and 50. And we are currently moving up. Then we end up moving right, and nr and c, the row, let's do the flip thing again. If we flip, we get here, so the row we need to add 50. So the row is nc plus 50, and the column is always 50. The condition in the inverse direction is if the column is equal to 49, and the row is between 50 and 100, and we are currently moving left. Then we end up moving down, and we inverse the operation again. So if nr equals nc plus, sorry, the row is always 100 firstly, and if nr equals nc plus 50, then nc equals nr minus 50. Okay, last pair. This one here. This one, remember, again, it's flipped, but it's basically the same thing we did on this side, so it's not going to be very hard. So the condition for this side is if nc is equal to 49 and nr is between 0 and 50, and we are currently moving left, then we end up moving right, and NR_NC is just equal to 149 minus NR and 0. And finally, if we move off this edge, the condition is NC is equal less than 0, and NR is between 100 and 150, and we are currently moving left. Then we end up moving right, and again, NR is 149 minus NR, and the column is now 50. Okay, before we proceed though, we're mutating dr and dc regardless, but if we hit a wall, then we don't actually want to change dr and dc. So we're going to cache dr and dc up here, cache dr and cache dc, and if we hit a wall, then we just simply revert the updates. And theoretically speaking, this should now give us the correct answer. List index out of range. Okay. Why? Okay. So we're getting a case where NR is 200, and this didn't result in a warp somehow. So let's take a look at our 200 case. So NR greater than or equal to 200. This case should have been caught, and NC is between 0 and 50. So that means that our direction is wrong. If NR is 1, so that was this edge here. Okay, so this here then should be a downward movement check. And let's see if that's the correct answer. It is. So yeah, this problem, it's very tedious, but if you can get your visualization down like this, which isn't too hard if you just label out the corners, then it's more or less a matter of just writing out all of the conditions and where they jump to. The thing that tripped me up was actually exactly this step here. I was manipulating the direction even if the part after the warp was a wall, which got me stuck for a long time. My warp logic was actually correct from the very start, although it didn't look quite this nice. So yeah, this is one of those problems where it's a lot harder in appearance and before you solve it, and then once you see the solution, it seems so easy. Like, the code is honestly not too long for this. It's under 100, and this part could probably be condensed a lot. The parsing also could be shrunk down a lot more. Like, overall, the problem is more tedious than difficult, in my opinion. I still did not have any fun with it, though. So, that's all for today's video. Thank you for watching. I hope you enjoyed and learned something, and I'll see you tomorrow for day 23.